Welcome to my structural designs and analysis tutorial channel featuring complete recorded sections on beam designs and its calculations. Hello, good day to you all. Today I'll be taking you on beam design and calculations. Taking rectangular beams as a case study, which we all know it can be simply supported or continuous, whereby these beams are often encountered in buildings where we have the lintels or roof beams, unlike the floor beams which are either L or T beams, which as a result will be casted monolithically with the slab. So these are the design procedures. The design procedures choose beam dimensions. In choosing the beam dimensions, unlike otherwise dictated for architectural reason or required to satisfy other requirements, width of the beam can be assumed to be 200 in building or the width of the wall. Preliminarily, the effective depth can as well be obtained from the span over effective depth ratio, which I made earlier in the previous class, whereby if we have the minimum depth required is the span, which we have here 3.5 meters divided by 26. The 3.5 meters divided by 26, that will be giving us about 155. Now about 155 or more millimeters. But from experience, however, from my experience, it is difficult for this depth to be adequate in resisting moment shear and local bonds at the ultimate limit state. Another approximate method is to use an equation whereby you use the d required equals to square root of m over 0.156 FCUB, and that can as well get you the depth required. And to obtain the overall depth, the cover reinforcement is added to it, whereby we have the H here. Okay, before I go to that, whereby we have the H here, you can get it from here, whereby we have the H equals to D plus cover plus stereo of diameter plus half main reinforcement diameter. Now there are some tables which shows there are some tables from BS code and IS code which shows the minimum depth required, and as regarding that, let me just make a look at one of our tables here, whereby you have H can as well be calculated as D equals to 3.50 D plus 50 millimeters, whereby we have the depth plus 50 millimeters. Now here we have to estimate dead loads and live load. Estimating dead loads, we all know that depth of dead load and its finishes can be estimated with the other imposed load. This load are expressed to this load are either expressed as uniformly distributed load or as point load, as the condition dictates. Partially loading may as well be experienced and in the analysis processes. Hereby we have to obtain in the analysis processes, which is the number 3 on the design procedure. The analysis, we have to analyze the structure and obtain the ultimate bending moment, the M, and the shear force. It is advisable to calculate the imposed shear force at the end of each span in order to limit the theoretical stirrup spacing to the distance where such is required and cover the remaining internal distance with stirrups at nominal spacing. This leads to considerable savings in the stirrups. And the design, here we have to calculate the ultimate moment of resistance and design for steel reinforcement, whereby we have the mu equals to 0.156 bd square, and whereby we have from there we can as well, if the ultimate bending moment is less than, or if the ultimate bending moment, the M, is less than the ultimate moment of resistance mu, M subscript U, then you have to the tensile reinforcement only is required and the lever arm will be obtained. But if otherwise, if the case is otherwise, the beams will be designed as doubly reinforced. So then we proceed to the lever arms, where we have the formula 0.5 plus square root of 0.25 minus k over 0.91, and the k value, which can as well be obtained from m over fcu bd square. And that for that. And as well, you can check the area of steel, where we have the as equals to m over 0.95 fyld or fyz, because z equals to l over ld. And a check which should be made to ensure that the areas of the reinforcement provided lies within the limit. For my steel, we have 0.15 less than equals to 100 as over bd less than 40. And for IE still we have 0.25 less than AS 100 AS over BD less than 40, and while for IE still we have 0.15 less than AS over BD less than 40. And if M is greater than MU, then the tensile and compressive reinforcement are required, whereby we have the AS bar and the normal AS. We have 2 area of C and 2K. And a check will be carried out on the steel ref as we provided earlier. Note that the compressive reinforcements, these are required and sometimes you can as well generate that from the numerical formula for evaluation parameter, since this helps in completing the design analysis. You have to check, and next is to check, that's for the design, and next is check on the shear stress and design for shear reinforcement, where if found inadequate. There you have to get the shear stress, shear force V, shear stress V over V BD square, and it should in no case should the V exceed 0.8 square root FCU. That's for that. And you have to calculate the minimum links required, the shear spacing and others. Now let's proceed to the design and the calculations we have here. Now these are the beam dimensions. Like I said earlier, it is from experience it's advisable we use 230, and not having a height, and 230 for a ground, since we are using a ground beam, 230 and 450 is okay. And yours might differ, whereby you have an increased depth of it, which will eventually affect the overall height. And the length, we have the length here 3.5 millimeters, 3,500 millimeters. The FCU, we are using concrete grade of 25 by 410. FCU 25, concrete grade 25 Newton per mm, while the steel grade is 410 Newton per mm square. Now for this, in the loading, we have the roof load to be 4.50 times 4 divided by 2, which give us 900 kilonewton per meter. We have the beam own weight, which is the depth 0.23 times breadth 0.23 times depth 0.45 times concrete own weight 24 kilonewton per meter and times 1.4, which is the dead load. And the beam finishes, we can as well use 0.60. The wall finishes, we have 3.47 times 2.77. 2.77 is obtained from a deduction of 230 mm beam, a 230 mm roof beam from 3,000 millimeters story height. That gives us 2.44 and times 1.4, which is dead load. This is the ultimate load here, where we have the summation of all the loads, where we have 26.53 kilonewtons. Reference can also be made to BS 399, IS 875. BS 399, the part 1 to 3, which have loading for building, dead load and imposed load, part 2 wind load and 3 imposed load, while the IS, which has part 1 to 5, dead load, imposed load, wind load, snow load, special loads and combinations. Now, part number 2. Here we have the analysis. Like I said earlier, we have to design for the ultimate moment, whereby we have m equals to ws square over 2 over 8. our W, which we obtain from here, the total ultimate load, which 26.53, like you can see there in the output, 26.53, and the length of 3.5 meters for the beam. Having this, we get a total of 40.62, and we have to calculate for the moment of resistance, like I said earlier during the analysis, in the third procedures, the analysis, where we have 0.156 FCBD square. The B is 230 mm, FC is 25 Newton per millimeters, and the D is obtained by H minus C minus S minus theta over 2. I'm sure you all know this. The H is the 450, which is the depth. The C is the concrete cover, 25 millimeters. S the stir up, minus 10, where we are using a stir up of diameter 10 mm, and a member of 16 mm, which is diameter over 2, which is 8. 8 plus 10 plus 25 gives us 43. A deduction of 43 from 450 gives us 407. And now, since we have this value at the end of the it, we have 148.587. Then, since this M is less than mu, therefore the beam will be designed as singly reinforced. Like I said earlier, then therefore tensile reinforcement only is required. If otherwise, it will be doubly reinforced, and tensile reinforcement and compressive reinforcement will be required. Here we have the lever arm. Lever arm equals to Z over D, and Z equals to lever arm times depth. The lever arm gives us is having a formula of 0.5 plus square root of 0.25 minus k over 9 is 0.91, where the k is the k value, and k is equal to m over FCBD square. Our m, which obtained from this design ultimate moment, m equals to 40.62, b equals to 330, and d equals to 407. Just a repetition of the output. Now, since we at the end of it we get 0.42, if k is less than 0.15c, the value will be used. Therefore, k equals to 0.42 is satisfied. Now let's go to our sheet. Here we have the k up to 0.042, the values of k correlating with the lever arm. Now we have 0.042, and we have lever arm of, if your k is up to 0.042, your lever arm will be 0.95. Let's see if we can get that from what we're analyzing. Now we have this. Okay, we have this, the lever arm. After the calculations, we have 0.5, calculating it, and we have this 0.095. Now, after doing that, we get to Z equals to LAD. Our LA is 0.95, since we can as well, for what we have calculated earlier, times the depth 407, and we have 386.650 millimeters. Now, x equals to, that's eccentricity here, d minus 7 over 0, d minus z divided by 0.45, and we get at the end of it we get 45.22 millimeters. Now, reinforcement. In this reinforcement, we have to calculate area of reinforcement, the shear, and check on the reinforcement itself. You can as well reference to BSc 10 part 199 table 8.3 appendix. I will show you that in the Microsoft Excel, one of the table in Microsoft Excel. Now, in this we have the M design ultimate moment, and 0.95 FYZ. The FY is the steel grade, which we will use 410 Newton per millimeter square, and calculating that we have 269.747. So here is the table. Since we have an area of steel required of 269.747 millimeter square, and using a member size of 16 mm, so that fall into this category of 201 to 207. So we have to provide for an adequate area of steel, which will be sufficient enough for the reinforcement. Here we will be providing for 804 millimeters, 804 mm square. So doing that, 804 millimeters square. Doing that, under 804 millimeters square, we have 4y, number of bar to be 4 that will be 4y16. So splitting that, we have 2y12, 2y16 bottom bars, top bars, and 2y16 bottom bars. You can as well reference that in this BS code here. Now we have to check on the reinforcement for mild steel, which is R16 or R16. We have 0.225 less than or equal to 100 AS, area of steel required over area of steel provided over B breadth times depth over less than 40, and that for high tensile steel, which is Y16, we have 0.15, which we'll be using 0.15 less than or equal to 100 AS over B this breadth times depth less than 40. Now calculating from that, we have 100 times 8 to 4 this, and as a result of that, we ended up having 0.8568, 0.858, which 0.15 is less than it, and what we got is as well less than 40. Therefore, that this area of steel design is okay. Now we are checking for the shear. The shear force V is ml over 2, which is a design ultimate moment times length over 2, an average of it, whereby we have 71.09 kilonewton. Now, having gotten that, we check for the shear stress. The shear stress is the shear force over BD, and we convert this to Newton, where we have times 10 raised to power 3 over the breadth times depth, and we end up having 0.75 Newton millimeter square. No, so now permission shear stress from table 6. Let's check from table 6. We have our shear stress to be, our VC to be 0.75 Newton per millimeter square. Now coming back to here, we have 0.75, and 100 over here is be the 0.75 to be this, and this is what we got now. This is what we got from that is 0.57. Since our depth is greater than 400 mm, so what we got is 0.57. What we'll be using is 0.057, and for this and for this and for this we'll be having, and for the shares for the share setup, we have SV equals to SV of SV over concrete grade, steel grade, V over breadth times depth. And now the shear stereo spacing is obtained by 0.5D, where we have our IS India Standard Code 45CACL 26.5.15. Its reference grade as 0.5D is the maximum diameter spacing, and 300 mm, and that for what we designed is 305.25 using depth of 47 millimeters. Now we have to provide for it. We'll be providing for Y10, since we're using 10 mm reinforcement at 2 legs at 300 center to center steel. Now with the accurate bond, since there is no redistribution, our beta is 1.0, and the factor of safety FL is equals to 2 over 3 concrete grade FY, area of steel required over area of steel provided. That has been listed in this output here in the output columns. Now we have this, and it resulted having 17.53 kilonewton. From B, since we are using plain bars, let me show you that. Since we are using plain bars and we are designing for tension only, since it is singly reinforced, the design is singly reinforced is 0.28. If it is doubly reinforced, we'll be considering the bars in tension and bars in compression. So for this, we are using bar in tension. Here we have where we have 0.28 square root of FCU, and at the end of the day we got 1.4 Newton per millimeters. We have 1.4 Newton per millimeters. Now going to the E, we have the factor of safety over pi over FCU FBU. We have our FBU to be 1.4 Newton per millimeters, and our FC to be 25 Newton per mm square per mm, and we have our pi to be 3.142, and we resulted having 668.72. And since there is no curtailment, the accurate length is fully satisfied, and as a result of that the design is okay. Here is the detailed design below. Here is the elevation and here is the section. The elevation here shows the two Y16 top bars and two Y16 bottom bars and the length. Here we have the, okay, let's calculate for the length. We have a 3,500 millimeters beam. Subtracting the concrete cover at both ends, we have 50, 25, 25, 50, and that's subtracting it for 35, we have 3,450. Dividing that divided by 300, we'll be having 11.5 or something near, and that will be approximated as 12, since we will be using a significant number of bars. 12 Y1001 300 mm center to center, and 2 Y1602 and 2 Y1603, the bottom bars and the top bars. We are sectioning through this A. Here is our section where we have the Y bottom, where we have the top bars O3, the bottom bars O2, and the links. You can see the link here. This is the link here, 0.1, Y10 is 0.1. So that's for that on the beam design and calculations. Thank you for watching. Like and subscribe to the channel for more videos and updates.